Okay, class, next topic. We did arc length. We thought about it approximately and then exact, and we had a formula for it. And now we're going to do something called a curtain interval. We have a couple different types of curtain intervals. We're going to start off with the first type, which is the most straightforward. And we're going to talk about a roller coaster defined by this space curve. So an R3 space curve, we got three components. We have a domain over which t is defined from -6 to 3. So let's go ahead and get an idea what this looks like to see how fun this roller coaster is. So I'm going to go to Calc-Plot3D. And we're going to take a look at, okay, so I've already entered it in. Our X, Y, Z components, we're pretty good at doing that now. Let's zoom out a bit. Okay, so here is our roller coaster and the direction of travel. Let's put a couple arrows in there. Okay, so we start over here. It's going uphill. It's not too windy, and then it's uphill, a lot of side to side, and we'll just end over there. Let's say it t equals 3. So I didn't pick a really good ending for this roller coaster, but you guys get to do that for one of the challenge problems at the end of chapter 2 to design a roller coaster, and you can even use piecewise defined functions, which will make it more interesting. Okay, the story here though for this section is that we actually want to build a support structure. So some of the original roller coasters, they had a almost like a wooden lattice. So from that blue down to the ground, which we're going to assume the ground is the XY plane, we actually want to define a structure. We want to know what is the area basically. And so let me put in another space curve so you can maybe see what I'm talking about with how the support structure would go directly from the blue down to the XY plane. So I need to add another space curve. Let's see, select space curve, and I'll just copy these same components. Second component of the space curve was -2t. And the last component of the space curve, the z component, was 5 minus 0.1t squared. However, we want this blue thing to blue space curve, which has some height, some z values, to actually be projected down into the XY plane. And so we actually want to force that z component to be 0. So this is the space curve that I want right here. I want z to be 0. And then I want my t to range the same thing from -6 to 3. And let's go ahead and enter that one. And let's change the color. So the one that's in the XY plane, let's make that guy red. Okay, so this is the one directly below it. So it's just like a shadow. If you were shining a light on that roller coaster, the shadow it would make from directly overhead down into the XY plane is this space curve. So I have two space curves. And really what I want to get is the area between those two. And that actually makes a curtain. And so there's a couple nice pictures in this section of your book. Yes, so the page entitled Roller Coaster. Let me stop the screen share. So roller coaster, and there is our space curve we just did in Calc-Plot3D. And then at the bottom down here is what the roller coaster and its shadow, the track or projection in the XY plane looks like. And what we're going to do is actually approximate that on the next page. So we want this nonlinear curtain, but we're going to actually start by thinking of it as a geometric or a partitioned wall, this one over on this side. So that is, again, thinking in the Calc-Plot3D visual. This is definitely this wavy curtain, and it's a vertical curtain, right? But we actually want to turn this blue and this red into their linelet approximations, and then get the area of the partition wall between those. So again, the pictures here really help. What we want to get, what we're going to start with an approximation, and then there's also a nice picture of the space curves. Actually, when they're projected into the XY plane, it's this nonlinear one on this side, but that actually has this linelet geometric approximation over here, which we are good at getting those. Okay, so that is the visualization, what we're trying to do. Now we want to get the exact area of that. And so maybe rather than writing stuff, because you already have it in your journals, is the box on the curtain integral page. At the bottom, there's this nice gray box that actually has everything we need there. So to get an exact curtain area, really all I need to do is take the arc length of the blue or the red. They're the same, exact same arc length. So again, the upper track that the roller coaster's on, or its projection down here, they have the exact same arc length. So I can take the arc length of either of those, and I can get that arc length in a couple ways. I can do it with the approximate formula. So where I'm actually just summing those linelet approximations of the tracks. And I'm doing that as n goes to infinity. And then I move, when I start doing that as n goes to infinity, I'm moving down to my exact areas, which are done with definite integrals. So I'm really taking the arc length, the exact arc length, times a height. So again, an exact arc length of either track, the roller coaster track at the top or its shadow down at the bottom. So those have an exact arc length that I can get with a definite integral. And then I need to multiply that by the height, right? To actually create the structure between those two, I need to know how tall it is at any given point. So sometimes this always stays flat in the XY plane, but sometimes it's taller than others, right? So I need to know those distances in this direction, those Z distances. So those heights though, Z distances are actually just given right here. So that's why this formula at the bottom is so compact and should make a lot of sense to you. We're really just doing this last one is the way to think about it. You're just getting an arc length of the projection in the XY plane. That's what we're calling R sub XY. Or you're taking the arc length of the plane curve in the XY plane, which only has two components then, a derivative with respect to X, a derivative with respect to Y, taking a square root, that's by the Pythagorean theorem, sum of the components squared, square root, multiplying by the height, Z. All right, so there we have it. That's an easy way to get a curtain area. It's just taking an arc length and then multiplying it by yet another dimension. Arc length actually is just this, well, it has one dimension in the T, so it's this one-dimensional thing. Multiplying by yet another dimension is our heights with the Z's as we go across. Okay, so for this roller coaster, we can set it up, but as usual, we're going to need a tech tool to do that. And so the setup would be that we're going to be taking an integral from our T limits -6 to 3 of the derivative of this in the X and Y component. So actually, let me make some space. Curtain area A, let's say, is going to be integral from -6 to 3, a dt, and we need to take our derivative. Not so bad, and we'll call it just with the X and Y, because again, those are the only components we care about. This third component we're zeroing out so that we're in the XY plane. And so we'll be getting a square root of a sum of components squared. But we have to make sure we multiply by the heights. So what goes right here is your Z. Those are the heights. And this is the arc length of the roller coaster. And our heights are this Z component, 5 minus 0.1 T squared. And then we need to take some derivatives. Not bad on that one. So maybe I'll make a little more space. Derivative of -2t is just -2. It's this first one here that requires a product rule. So maybe let's actually just write that right here. X prime of t is going to be the first times the derivative of the second. So that'll be a cosine -4t times a -4. Squeeze that in there. Plus the second times the derivative of the first. So that's a 0.4 e to the 0.4 t sine -4t. So all of that needs to get squeezed in here. And then we need to do that integration. Again, not one we can do by hand. We have to use a tech tool. We've practiced that last time. So you can use Wolfram Alpha, ask it to integrate and just type all this in. And there is no shortcut this time. You can't just say give me the arc length because you need to make sure you're multiplying by the height. So when you ask Wolfram Alpha to integrate this, you get 80.79. Again, what that represents is the area of the curtain that goes from the roller coaster's track, which you're actually riding on the roller coaster, and then the projection of that same track down in the XY plane. So we build a support structure with that units squared because it's an area, whatever those are for this problem. Okay, so let me quickly summarize and then we'll move on to our other types of curtain integrals. So for our first curtain integral, we are going from a space curve to its projection in the XY plane. We want to get the area of that curtain. That area of the curtain is really just getting an arc length. So we have our, hopefully you see here, this is the arc length piece of it. And then you multiply it by a height. And that height is given by the Z value of your space curve, this component here. Okay, so that's the last piece of that puzzle. Now we're going to go on to two other types of curtain integrals. We're going to have curtain integrals between a space curve and another space curve that doesn't have to be in the XY plane. So yet another space curve. And then we'll go between a surface, so something like our surface to a space curve, or a surface to a space curve above. So we'll take those extensions of curtain integrals up in the next video.